Okay, so yeah, welcome back. So yeah, I will continue the discussion on the correlation, electron correlation or electron interaction in physics. So to recall the discussion yesterday very briefly. Oh, okay, I should. Yeah, so yesterday I discussed about ferromagnetism and pointed out that interaction is really necessary to realize ferromagnetism. And there is a simple mean field approximation analysis, and you consider Hubbard type model, for example, and treat the interaction term in mean field approximation. Then you can see that by generating the spontaneous magnetization, you can actually lower the interaction energy. But by generating spontaneous magnetization, you need to create an imbalance between upspin and downspin electron population. That increases kinetic energy generally. So within this framework, the question whether ferromagnetism occurs is based on the comparison between the lowering interaction energy versus increase of the kinetic energy. And in this approximation, the condition is that this density of state at the Fermi level times the interaction. If this product is greater than 1, then actually you can lower the total energy by creating a spontaneous magnetization. So in this case, you can say that the ferromagnetism should happen. But of course, this is within the mean field approximation, so it may or may not be correct, but this is the picture. So yesterday I also pointed out that if you take this formula literally, then for any density of state, if you send U to infinity, then you expect ferromagnetism, but it's not generally true. But you can also get some inspiration from this formula that you can try to make this density of states at the Fermi level very large. So one of the such a extreme limit is so-called flat band. So in some material or some model, you have completely flat band, which means that the energy of single electron is constant in entire Brillouin zone, means that the single particle energy doesn't depend on the momentum. So in that case, exactly at the energy of this flat band, you have many states. So in this case, the density of states diverges. It becomes infinity theoretically. So in this limit, the Stoner criterion is actually satisfied because D of EF is infinity. So infinity times anything is larger than 1 if there is even small interaction, the positive interaction. So of course, again, this Stoner criterion is very crude. It may or may not be correct, but this suggests that maybe we can get the ferromagnetism in flat band system when the Fermi level is at the flat band energy. And so this is also natural in some sense, even if we forget about the Stoner criterion, because this slide I copied from yesterday's talk. So let me recall why it was difficult to realize ferromagnetism in fermion system was that usually there is a band structure. The single particle energy depends on the momentum, or even if you lose the translation invariance, then you cannot no longer talk about band. But usually there is a distribution of single particle energy among single particle eigenstates. Then if you want to construct a many body ground state, many electron ground state, you put electrons starting from lowest single particle energy state. Then each level can be occupied by upspin electron and downspin electron. So if you keep filling the lowest energy single particle energy states, then you end up with a non-magnetic state because each state has upspin and downspin electron. So in general, the free non-interacting electron system ground state must be singlet or non-magnetic. So it's just a paramagnet. So in order to realize ferromagnetism, you need to overcome this tendency by interaction. So that was a difficulty. But in case of flat band, you have a lot of single particle energy state with exactly the same energy. So as long as the number of electrons is less than the number of these flat band states, you can put upspin electron to each single particle energy state. So like this. So you don't have to put downspin electron to those states, as long as number of electron is sufficiently small. So in this case, okay, so this state is obviously ferromagnetic state. So you can see that if flat band is the bottom band of the system, then you have a lot of lowest energy single particle state, and you can put only upspin electron to each state. Then this is ferromagnetic state, and this is obviously among the ground states of the system in the non-interacting limit. But of course, in the absence of interaction, you cannot say this is ferromagnetic, because you can also put downspin electrons in this system, in this flat band, lowest energy flat band states. So it's more like a paramagnetic. Any spin configuration can be ground state in this flat band system. So it's not yet ferromagnetic state, but unlike in generic fermion system, electron system, in case of flat band system, at least ferromagnetic state is one of the ground state among many other states. So now you introduce the interaction, and if this interaction selects this ferromagnetic states at the ground state and lift all the other states to excited state, higher energy states, then finally the system is ferromagnetic. So even in flat band system, you still need interaction to realize ferromagnetism. But the starting point is easier. In generic system, the ground state was completely non-magnetic, and the ferromagnetic state was in higher energy. And somehow you need to bring down this ferromagnetic state in energy in order to realize ferromagnetic in the ground state. But here, the state at the starting point, ferromagnetic state is already at the ground state among many other states. And you need to just lift all other states to high energy. So in this flat band system, in principle, you can have a ferromagnetism even for infinitesimal, very small interaction. But of course, it's non-trivial question whether interaction really chooses ferromagnetic state as a ground state. But there is we can hope, and actually for some particular systems, it was shown that indeed for flat band plus interaction, the ferromagnetic state indeed becomes a ground state, which was shown by Mielke and Tasaki and others. Yes.
So in this case, Kant's first rule is assuming that maximize spins. So irrelevant of whether it's down or up spin, you're still breaking time versus symmetry. You still have net magnetization. Is that not the primary ground state that you find?
Sorry, maybe I didn't get the good. So if you apply so-called Hund rule to this kind of system, then yes, the ground state should be ferromagnetic once you introduce an interaction. But so the question can be also phrased like, is this Hund rule really valid in this flat band system? Yeah. And indeed, for some systems, so-called Hund rule really works, but it's not totally trivial. And, indeed, Mielke discusses the relation between this and the Hund rule. Yeah. Pardon me? Yeah, of course, it depends on what exactly is the interaction. But for simplicity, I will, for simplicity, we can ask the question for Hubbard type model with on-site interaction. But of course, you can introduce other types of interaction. Then, of course, generally the answer depends on the type of interaction. Okay. So yeah, there are many results on this so-called flat band ferromagnetism, and I'm not going into much detail about this, but I just want to introduce one of the remarkable results. And I'm not going to, that proof, but I just want to introduce one very remarkable result by Mielke. He also has several other papers, but this is one particular paper published in 91. So yeah, he has some theorem. So this G is some graph, and the graph is terminology in mathematics, so-called graph theory. But you can imagine G as a lattice, and given the graph or lattice G, you can define a so-called line graph. In physics terminology, this line graph is usually called a dual graph, dual lattice or something like that. And so if you consider Hubbard model on this line graph, then if number of electrons satisfies this number of electrons is exactly given by this number of edges minus number of vertices in the original graph or original lattice, then actually he proved that Hubbard model on this line graph, dual lattice with on-site repulsive interaction has ferromagnetism, which means that the ferromagnetic state is indeed a ground state in the presence of interaction, and all other states are higher in energy. So this theorem is very nice because it has many applications, especially to one of our favorite lattice, which is Kagome lattice, because okay, so the picture is not so clear, but perhaps many of you are familiar with this, but you can start from honeycomb lattice, like a graphene. So in this figure, it's this honeycomb lattice is drawn in gray, so it's not very visible, but you can first imagine this honeycomb lattice. And honeycomb lattice has atom. Like in case of graphene, you have carbon atom at this vertices, each vertex with 3 gray lines. So this is honeycomb lattice. But he considers the Hubbard model on line graph, which is dual lattice in physics. So dual lattice is constructed by putting the site or vertex at the center of each edge of the original lattice, the honeycomb lattice. So you put the site of vertex at this black circle position, and then you connect these dual sites, dual vertices, if these gray original edges or links connect to the single same original site. So then this site, dual site and dual site is connected by this edge or link, because originally this gray edge was connected to the same site in the original lattice. So in this way, you can construct a dual lattice or a line graph or the honeycomb lattice. And this is nothing but the Kagome lattice, which we are familiar with. And this is indeed, so we can consider the Hubbard model defined on Kagome lattice. And in the absence of interaction, so this is also well-known result in physics. So maybe you know this, but if you consider tight binding model on Kagome lattice, just a nearest neighbor hopping on Kagome lattice, and for the moment forget about the interaction, then you can obtain the dispersion relation on Kagome lattice. And this is a dispersion relation, and indeed the bottom band is completely flat. And so this Kagome lattice has flat band. And so this is very well known. But what Mielke proved is that, okay, so this flat band of Kagome lattice also follows from this general construction line graph and so on. But not only that, once you introduce on-site repulsion on to the Hubbard model on Kagome lattice, then he proved that indeed a ferromagnetic state is the unique ground state, and all the other states are higher in energy. So yeah, this is again his theorem, and this is a standard Hubbard model he considered, and he want to consider this standard Hubbard model on line graph or dual lattice of some lattice. And one of the example is Hubbard model on Kagome lattice, and the number of electron has to satisfy certain exact number in order to use this theorem. But so it's given by number of edges minus number of vertices, but the number of edges and vertices of the original lattice, that is honeycomb lattice, not Kagome lattice. So in honeycomb lattice, each unit cell has two sides, A side and B side, but there are 3 edges per unit cell. So if you subtract E minus V, so basically this is given by number of unit cell. So if the number of electron is equal to number of unit cell plus 1, then you can fill this bottom flat band completely. And plus 1 is a bit of subtlety, but it's also maybe well-known result that the bottom band is completely flat, but there is a second band which touches the flat band at one point in the Brillouin zone. So you need to have electron number plus 1 in order to fill this extra state due to the touching of the second band to the flat band. Anyway, that's a small part. But anyway, so what he showed was this more general theorem, but one nice application is to Kagome lattice. So he proved that if you consider Hubbard model on Kagome lattice, just a standard one, on-site repulsion, then for any positive repulsive interaction U, this Hubbard model on Kagome lattice has ferromagnetism. This is a really rigorous result. And it's also kind of natural because of this flat band. Yes.
What is the original? So cognitive systems are also highly sought after for quantum spin highly frustration.
Mm-hmm.
How do you get that frustration to contradictory, right? You have here from ferromagnetism.
Okay, so I I'm not sure I have adequate answer to your question, but one okay, so we start really from this Harvard model, not the anti-ferromagnetic model, and also so if you start from this Harvard model and electron number is like one electron per site, then in a large U limit by standard perturbation theory, maybe we have a anti-ferromagnetic Heisenberg model on Kagome lattice, which is frustrated model, like you say. But I think the electron filling is different here because this is here electron number is one electron per unit cell, meaning no, but let's see. No, I may confused. But so for Kagome lattice, what is the number of yeah, but okay, so this is number of unit cell in original lattice, honeycomb lattice. But is that the same? Sorry, so I have to ask a basic question. So for Kagome lattice, the number of so what is the unit cell? The unit cell is okay. So unit cell consists of maybe these three sites, right? Yeah, three, right? Then yeah, 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 yeah. Yeah. That is a point I wanted to make. Yeah. Thank you. Yeah. So I think this anti-ferromagnetic Heisenberg model on Kagome lattice and this ferromagnetic state actually corresponds to different physics. Yeah. So we can expect different physics. Yeah. So this feeling corresponds to just filling the bottom flat band by only upspin electrons. Okay. So yeah, so this is quite nice because Kagome lattice is very natural, and Harvard model on Kagome lattice is very natural model, and for this very natural model, this theorem applies, and the ground state is really ferromagnetic. So this is one of the nice example of rigorously proven ferromagnetism, and Milke and Tasaki also several other theorems which can be applied to some different examples. Okay. So that is one nice thing, and maybe okay. So I maybe forgot to emphasize, but so this is one route to realize ferromagnetism, but this is also suggestive of one general strategy to realize a so-called strongly correlated system or interaction-dominated system. That is, if you have flat band or nearly flat band, then kinetic energy is suppressed or almost frozen. So within the flat band, any interaction is very strong, very dominant. So this is generally, uh, general strategy to realize so-called strong correlation physics. And other well-known examples include a quantum Hall system, because in the magnetic field, you have random levels which are completely flat, at least in a continuous space. So that's why in quantum Hall physics, interaction can play a important role, and you can realize fractional quantum Hall effect, for example, in which the interaction is really essential. And another interesting topic, which is studied very vigorously in recent years, is twisted barrier graphene. So again, by twisting the angle between two layers of graphene, you can make the flat or almost flat band. And within this nearly flat band, the dispersion is suppressed, then interaction can become dominant. So this flat band ferromagnetism is one of the examples, demonstrating that in flat band you can suppress the kinetic energy, then interaction can play an important role, even if the original parameter, interaction parameter, looks small. Okay. Then now I want to come back to another route to ferromagnetism. This was also rigorous theorem, but kind of looks very peculiar, because you have a Hubbard model at U infinity limit, and then just dope a single hole. Then this single hole becomes mobile, and then Nagaoka proved that the ground state of such single hole system is actually ferromagnetic, which is also very interesting. But at this point, it's kind of, I would say, pathological, yeah, how to say, this is proved only for single hole, even for very big system. So it's not like a thermodynamically stable ferromagnetism. So of course, the natural question is, okay, so for single hole, you have ferromagnetism, but what about finite hole density for very large system? So if you go to very large system, even for tiny hole density, you must have many number of holes. But once you introduce two holes, then this Nagaoka theorem already fails. So it's kind of very fragile. Now, of course, proof fails, theorem no longer hold, does not mean ferromagnetism lost. Sometimes you cannot prove something as a theorem, but still the system may show that property. So there were several numerical studies, trying to extend this Nagaoka ferromagnetism to finite number of more number of holes or finite hole density. Yeah. 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 Mhm. Yeah. 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 That's the point I'm coming to that. Yeah. 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 Thank you. So yeah. So yeah, indeed. So this proof fails for or more holes, and why this proof fails is exactly because this assumption part of Perron-Frobenius is no longer satisfied. Because if you have two or more holes, then by hopping these holes sufficient number of times, you can exchange these two holes. Then if you exchange two fermions, you get a minus sign. And once you get a minus sign somewhere in the matrix element, then you cannot apply Perron-Frobenius theorem. So this shows that this difficulty of extending Nagaoka ferromagnetism to finite hole density or even to two holes is related to the original statement that Fermi statistics basically disfavors ferromagnetism, because in order to realize ferromagnetism, all the electrons should have the same upspin, let's say, and it's kind of bunching. But fermions are against bunching. They want to take different states, right? Yeah. Yeah, theorem, that particular theorem fails, but he did try to extend the theorem to some finite, the different hole density. He did prove some theorem which works for range of electron density, but maybe not for that particular case. I don't remember, but yeah, please consult his papers. Yeah. Okay, so the fundamental point is that this Fermi statistics basically doesn't like a ferromagnetism, because ferromagnetism means that all the electrons should take the same spin state. So that suggests a very simple way of realizing ferromagnetism. So the Fermi statistics was the culprit. So if you consider the spin 1/2 particle, but those are bosons, then actually it's very easy or to realize ferromagnetism, because rather generic interacting model can have ferromagnetic ground state if those electrons were bosons. Of course, bosonic particles cannot have a spin 1/2 according to spin statistics theorem, but it comes from relativity. So in non-relativistic system or condensed matter AMO physics, we can imagine spin 1/2 boson, and sometimes you can realize at least for pseudo spin 1/2 boson. And indeed, so this is, I think, very simple to understand, but it was only discussed relatively recently. Okay, well, already more than 20 years ago, but in the long history of this physics, it's relatively recent, I would say. So there is a general theorem by Eisenberg and Lieb, proved in 2002. And the lattice version was discussed by Freda Johann company in 2005. And basically, they proved that if you consider spin 1/2 bosons, then very generic interacting system. There are some conditions, but for very generic system, indeed the ground state is ferromagnetic. And so proof is, again, if you really want to prove the theorem rigorously, there are some technicalities, but the basic idea is very simple. So again, let's consider, so in continuum, we can consider many particle wave function. And again, many particle wave function consists of the orbital part and the spin part, and the total wave function is its product, or maybe sum of a product. But for generic interacting many particle Hamiltonian, the ground state wave function should be again nodeless. Nodeless means that the wave function can be taken positive everywhere. I mean, for any configuration of those particles. So those are positive wave functions for, the Hamiltonian, which is symmetric under particle exchange, should be also, this wave function, orbital part should be symmetric under particle exchange. And for boson case, the total wave function should be also symmetric under any exchange of particles, which means that, yes. Yeah. Yeah. Yeah.
Does this require the kinetic energy to be p squared over 2m?
Well, yeah, for p squared over 2m, this holds for some generic interaction. Yeah.
But for this tight binding models.
Yeah. If the tight binding model satisfies certain connectivity, it also holds. And indeed, in the next slide, I will show the lattice version of the proof, which is essentially equivalent, but yeah. But the first continuum version, so the total wave function should be symmetric under particle exchange, and the ground state of the many particle Hamiltonian should be positive, nodeless, then it must be symmetric. Then the spin part must be also symmetric under particle exchange, because this part is symmetric. The total wave function must be symmetric, so the spin part must be also symmetric under particle exchange. Then if the spin wave function is symmetric under any exchange of spins, then its total spin must have a maximum value. So if you have n spin 1/2, then symmetric total wave function means that the total spin is n over half, which is a maximum. So this means that the ground state indeed must have a maximum spin, which is ferromagnetic state or saturated, maximally ferromagnetic state. So this is continued version of proof, but yeah. So there is a question. So I want to mention briefly about equivalent but direct argument for lattice model. So actually, in a second paper I mentioned in Fred Johan and company paper, they discussed this spin 1/2 Hadrocker boson on lattice, generic lattice. So again, they consider U infinity limit. So then the basis state of the total Hilbert space consists of some conflation. And in each conflation, each site is occupied by either a hole, that means the site is empty, or this site is occupied by upspin electron or downspin electron. So 3 possibilities. And each site can take one of these 3 states. And you need to satisfy total number of downspin, upspin. So number of upspins and downspins are conserved separately. So we can consider the fixed sector or subspace. So we can consider number of upspin electron is equals to number of downspin electron subspace. And then we have just a hopping. So upspin electron can move into empty site, and downspin electron can move to empty site. And that is the only thing Hamiltonian can do. And for appropriate lattice Hamiltonian, all the matrix element of this hopping can be made negative or 0. So, and also for square lattice and so on, you can connect all the basis states by moving around these holes, like in 15 puzzle I mentioned yesterday. So in 15 puzzle, you have just one hole. But if you have more holes, it's actually easier to reach other conclusions. So anyway, once this connectivity condition is satisfied, then we can again apply Perron-Frobenius theorem. So the ground state is given by linear superposition of these basis states, but the coefficient is all positive, thanks to the Perron-Frobenius theorem. So again, such a wave function, which has all positive coefficient, must be symmetric under permutation spins. So again, this means that the total ground state must have a largest possible total spin quantum number, which is saturated ferromagnetic state. So essentially, this proof and the continued version of the proof in the previous slide is equivalent. But yeah, technically, if you want to be rigorous, you can apply separate argument. Anyway, so this is maybe once you realize it's kind of trivial, maybe, but it's still nice, It's has been very, very challenging to realize a ferromagnetic model, but that was basically because electrons are fermions. So if electrons were bosons, then it's rather natural to have ferromagnetic ground state, and it's related to very nature of fermions and bosons. Bosons tend to bunch, take the same state. And if all the bosons take an upspin state, it's already ferromagnetic state. Okay, that's kind of interesting. But you may ask, but the real electrons are fermions, not bosons. So whether this bosonic ferromagnetism, this bosonic ferromagnetism anyway relevant for real electron physics? That's maybe next question. And I would say yes, because actually you can turn electrons into bosons. although real electrons are fermions. And this was indeed already discussed for many years in the context of quantum Hall physics. That is, in quantum Hall physics, quantum Hall effect, you have strong magnetic field, and electrons are moving under this strong magnetic field. And sometimes they form a very stable quantum Hall digit. And one of the approaches to understand quantum Hall physics was by so-called flux attachment. That is, you already have a strong magnetic field in the background, and then electrons are moving. And you can imagine, actually, this magnetic flux may be attached to electron. And now the composite particle of original electron plus flux can maybe move around. And indeed, if you consider magnetic flux quantum, H over E, and attach this to fermion, then composite particle of this electron with flux actually behaves like a boson. So this is why. So actually, this flux quantum H over E is such. This is determined such that if you have this blue particle, and here this red circle represents a flux of H over E, and this blue particle has charge E, like electron. And if you move this particle around and come back to the original place, then actually what you get is Aharonov-Bohm type phase. But this phase is 2 pi. So if you do that, phase 2 pi is equivalent to nothing. So it looks like nothing happened. But actually, going around this flux once is equivalent to 2 exchanges of particle, because we can think like in this right panel. So this is a flux, and this is particle. And now I want to move this particle, but only 180 degrees. I don't make a complete circle, just make a half circle. Then this particle comes to the opposite side. But in this process, the phase you pick up is just pi, because it's a half circle. So for full circle, you get 2 pi. So for half circle, you get a phase pi. After this, my particle is on the left-hand side, left of this flux. So now just you can shift this pair of particle and flux to the right. And by shifting to the right, you find my particle here and my flux here. And if you do that, you exchange the location of this particle and flux. So this amounts to the particle exchange. So of course, in this picture, flux and particle look, not equivalent. They are not equivalent. But if you consider composite of particle plus flux, then you can do this 180-degree circling and then shift. Then you can exchange these 2 particles. And on this parallel motion, you don't pick up any AB phase. So only phase you pick up is this phase pi. So that means that if you exchange 2 composite particles like this, then you get phase pi. So if original particle are fermion, by exchanging these 2 fermions, you get phase pi, but you get another phase pi from this flux AB effect contribution. So the pi plus pi is 2 pi, and the 2 pi phase is nothing, which means that if you exchange these composite particles, then you get phase 0. So which means that the composite particles are now boson. And this kind of flux attachment argument has been used in many problems in quantum Hall physics. And then it's natural to think like, okay, now if you have a flux, you can attach the flux to this electron. Then electron can be turned into boson. Then if electrons were bosons, then then the ground state should be ferromagnetic. So that is at least naive expectation. But of course, whether this flux attachment really works is a highly non-trivial problem. This part, there is no theorem or anything as far as I know about this. This is very heuristic argument, very attractive, but whether this really happens is a highly non-trivial problem. But we can, once this happens, then we can predict that the ground state of my electron system under very strong magnetic field background must be ferromagnetic, and we can test this prediction. And yeah, indeed, we did this some time ago, but actually it's like 20 years ago already. But I want to introduce this one of my very old works. So we just try to realize this model in lattice model. So we can consider, so there's a typo due to conversion from both sides. Sorry, this is U equals infinity Hubbard model, not U equals 1. Sorry about that. So we consider U infinity Hubbard model on square lattice with this magnetic flux background. But to simplify the problem, we don't introduce Zeeman coupling. Of course, if you have real magnetic field, then the spins may be polarized by magnetic field, and then the problem is trivial. But we don't introduce Zeeman coupling, just orbital coupling. But and then for square lattice, we can introduce gauge field so that we have some flux per bracket phi, flux phi per bracket. And if we go to U infinity limit, so double occupancy is forbidden. So we have only hopping term with the phase introduced by this vector potential. And the hopping can occur only if the hopping is towards the empty side. And then we can study this model at least by numerical diagonalization. And so this is a result. And this result, so first this two-dimensional plot, and the horizontal axis is density of electron, number of electron per site, and the vertical axis is the flux per bracket. And the result is color-coded. So this color represents the total spin of the ground state. And so this is the exact diagonalization study. So this is relatively small cluster. So this result is for 4x4, 16 sites. This is for 18 sites, and this is for 20 sites. And the blue color means that the total spin is 0. So it's a non-magnetic ground state. But this red color means that the total spin of the ground state is given by the maximal possible total spin. That is, if there are n electrons, total spin, largest possible total spin is n half. And the red color means that the ground state indeed has such a largest possible total spin quantum number. And so there are some random looking fluctuation, but there are some regions where you have a red color. Red color means that the ground state is ferromagnetic, at least within this small system size. And there are basically two regions of the ferromagnetism, saturated ferromagnetism. So one is on this left-hand side, this triangular region. But there are also red colors at the high density region, close to half filling along this line. So let me first discuss this triangular region. So yeah, so we can maybe start from non-interacting limit, although the model we studied here corresponds to U infinity limit. So at the limit of U equals 0, non-interacting limit, this is just a tight binding model on square lattice with some magnetic flux per unit cell. And this is the famous so-called Hofstadter butterfly problem. And if you have fractional magnetic flux, then magnetic unit cell is enlarged. So as a function of magnetic flux, the energy spectrum shows fractal behavior. It's a very famous result. So there is some lowest energy state for given magnetic flux. And overall, the energy spectrum shows a fractal structure, but there is some lowest energy branch for generic value of magnetic flux. And this can be understood as lowest lambda level in continuum limit. So in really continuum space, the lowest lambda level is always flat, but here we are considering tight binding model on square lattice. So in the presence of lattice or periodic potential, this lowest lambda level is split. Actually, this kind of perturbation theory starting from lambda level, adding the periodic potential as perturbation was discussed in the original paper by TKN. But anyway, so we can regard this lowest energy branch as lowest lambda level, correspond to lowest lambda level. Actually, even within this lowest lambda level, there is a fractal structure, but these can be regarded as subbands coming from lowest lambda level. So lowest lambda level is a single level in continuous space, but once you introduce the periodic potential or lattice, then this lowest lambda level is split into subbands. But still, the dispersion among the subbands are relatively small, at least especially in the region where magnetic flux is small. So what we found in the ferromagnetism found in this region roughly corresponds to filling these lowest lambda level subbands. So in this case, there are still some dispersion, but there's still some dispersion, but it's relatively small. So maybe we can interpret this as a kind of variation of a flat band or almost flat band, narrow band ferromagnetism. Density of state at the Fermi level is still large. But we also found a ferromagnetic ground state at a higher electron density, like this region. And in this region, it's difficult to understand this based on the band structure, because near half filling, you need to fill almost all the bands. So there is a big dispersion. And to realize ferromagnetic state, the polarized electrons must occupy this wide range of energy bands, which is not easy to understand, at least starting from this non-interactive limit. So I would argue, okay, so there may be alternative explanations still, but it would be most natural to understand this ferromagnetism observed along this diagonal, especially in this high density electron area as a result of statistical transmutation, because exactly along this diagonal, the flux matches the electron density. So you can attach one flux quantum exactly to one electron. Then if that happens, electrons become bosons, and then you can forget about magnetic flux. And that exactly happens along this diagonal. So I would say, yeah, this is maybe most natural interpretation. So, okay, so let's skip this part. We have some other evidence, but okay, so to summarize this part, okay, again, sorry about that typo. This is not U equals 1, but the U infinity limit of Hubbard model on square lattice with background magnetic flux, but without Zeeman coupling, just a coupling to orbital part. Then saturated ferromagnetism is numerically observed in two regions. One is in the low electron density region, where maybe we can understand this as a variant of flat band or narrow band ferromagnetism, where the density of state is large at the Fermi level, coming from the Landau level type, nearly flat band. Yeah, but at high electron density part, we still find a ferromagnetic ground state along this diagonal in this two-dimensional parameter space. And in that region, it's difficult to understand this ferromagnetism as a result of this high density of state or narrow band, nearly flat band picture. But once you accept this statistical transmutation due to flux attachments, then it's rather natural to understand this ferromagnetic ground state. So yeah, I still think this is maybe natural interpretation, which also supports this flux attachment statistical transmutation picture, at least in some cases. So yeah, I mentioned that so there is a famous Nagaoka ferromagnetism, nice rigorous theorem for U infinity Hubbard model, but it only applies for single hole doped into half filling. And it has been difficult to extend this Nagaoka ferromagnetism, but yeah, people usually tried to extend in this direction. That is, usually ferromagnetism is discussed in the absence of magnetic flux, and people try to lower the electron density from half filling. But at least looking at this picture, you know, indeed, a Nagaoka ferromagnetism corresponds to this point because you doped single hole to half filling. But if you go to left without flux, then you lose a ferromagnetism. But if you have magnetic flux, you can move to the diagonal direction. That is, as you change the electron density, you increase the flux, then you can attach this magnetic flux to electron, then transform electron into boson. Then bosons with spin 1/2 shows ferromagnetism rather naturally. And this may be one way to extend Nagaoka ferromagnetism. But even if we forget the Nagaoka ferromagnetism, as I mentioned, once you can transform electron into bosons, then for bosons, ferromagnetism is very natural. You know, maybe I would say it's rather difficult to avoid ferromagnetism in case of bosons. So okay, so I'm running out of time. So I hope I convince you that there is a strong relation between quantum statistics of particles and ferromagnetism. And so in that sense, ferromagnetism is one of the phenomena for electrons, which are fermions. Interactions are really essential to realize a ferromagnetism. But if electrons were bosons, then it's very easy to realize. Yeah, thank you very much. Well, okay, so that's good question. Yeah, I don't know the answer. Yeah, this mapping itself is kind of tricky. So yeah, we are kind of assuming that after doing this flux attachment transformation, you know, in terms of the new composite particle, the interaction is still local. That's kind of belief, I think, but not easy to prove.